This was my fault. Basically, in the morning I took too much time doing the other two presentations. So I'm going to present here some short, very short tutorial on how to project simulations. So it actually shows some of the things that may have been missing in the morning. So here I already have a structure prepared. It is from NT19, which is a protein that's normally used in folding studies and stuff like that, and the trajectory. And I'm just going to load it, the structure, read the XCC, filter it, and view it, okay? So that you can. So here, what you're going to get is the. I press F11 to have it first. We're going to see the bar. Now, control minus. It's okay. So, yeah, so we have here, it's just 10 frames. This is just for showing purposes, okay? So you can see that the protein is moving around and stuff like that. And one of the things that we're missing in the morning to talk about was, so someone was talking about wrapping and alignment in the trajectory. So we know that the protein goes through the periodic boundary conditions, and it's not aligned or anything, so it tumbles a lot during the simulation. So actually I have these molecule functions, wrap and align. You can also see them in the documentation. And they can use it to wrap the periodic boundary conditions and to align the protein given appropriate selection type. In this case, I think that for this case, protein and name CLF is okay, which is many people use it. So and then we can do this process of visualize it again, and then now you see that basically it's no longer fluctuating around, it's already aligned, and okay, this is just an extra that was missing from the morning, I guess. Okay. So now we're also going to take, so actually Stefan developed basically this part of the tutorial, and so we have here the crystal structure of the so this is basically, we are loading up the crystal structure of this protein and TL9, which is the corresponding one. And that simulation that we have is like unfolding. It's like it's a simulation where you have, I think it's at melting temperature. No, it's at melting temperature. Okay. So here it's when it's folded. So you can see that's different from the movie that we're seeing. So we have been talking a little bit about metrics, and now we are going to show a bit something that we can do with metrics. So basically, we have this, and if you check the documentation, we have these things that we call projections, and basically there are many of them. One of them that we're going to showcase here too, which are metric RMSD and metric dihedral. So, but this normally, when we've presented this many times before, we have presented always this as a standpoint as for dimensional reduction. So we have too many coordinates in space, and first, before we go to Markov models, we first try to find some metric that makes sense for the problem that we have. We try to reduce it to dimensions that way. Then after that, we do some further dimensionality reductions with Tika or something like that. And then that's when we do clustering in Markov model, okay? But I think that most of the times we forget about this initial step. And we think that many people are interested in seeing how these metrics behave and how can they plot them and access them. What do they mean? So we have this metric RMSD, which is an object which is uses a container which is called metric data to store all the data. The data is stored there, but then there are different ones. So metric RMSD, then you have metric dihedral, metric distances, and others. Some of those are already shown in other presentations. So here, what we're going to do when we do this, we're just going to do metric RMSD against the crystal structure, okay, and then giving this selection. And then we just do metric.project which basically just takes the whatever metric we already have, okay, on metric. We can set up more than one using the other procedures, but here we're just using one. So after we select the type that we want, metric RMSD, then we do the projection, okay, which is this project method. And then as the output, we get a data structure that we can then analyze, okay? This proj, which is a projection, is a data structure. And then we can actually plot it. And here what we are going to do in this plot is basically just show the RMSD, which is taken from this project data, the RMSD along time, okay? And we do that basically using the F step of the molecule and then using a range of the length of the projection, because the length of the projection is the number of time frames, right? Yeah. And you multiply it by the time step, so it gets...
Well, yeah, no, I just wanted to mention the proj here. So whatever project, it has to be a two-dimensional NumPy array, where where the y-axis is your frames, and sorry, but the first index are your frames, and the second index are your dimensions. Mm-hmm. So in this case, it's a one-dimensional projection because RMSD is just one number. Mm-hmm. So it's going to be the length of this vector will be the number of frames in this case.
Which means the trajectory. You just here through this multiplication, just convert the number of frames in time.
Yeah, in nanoseconds. Okay. Yeah.
So. And then we just set some labels, okay, for it to be nice. So normally what you're used to, so this is basically the same simulation that we're seeing, so 10 snapshots, but since it's already a folding simulation, normally what you see is that a normal RMSD plot, it starts here and it starts, for example, for a protein, it starts until it equilibrates, right? So a bit different, but basically it's just to showcase how you can actually plot one thing that is one of the most simple plots that everyone does when they start to do MD simulations. At least that's what it is with me. What I used to do back in the days, I guess, when I started working in MD. So I think that's one other thing, an important thing to talk about is, and something that Stefan actually took some time to implement, was the meaning of the what are the meaning of these dimensions that we project, okay? So, here, so I'm going to jump here directly. I don't know, I'm going to jump here directly to the get map. So, because here we remove the scene lists, right?
Yeah, we'll present them later.
Okay. So Stefan will present them later. The example here I'm just showcasing. Stefan will present later the case where you have scene list and you can do this on a list of simulations, okay? Here we're doing something simpler, which is just within simulation, but basically we can use this method that is called get mapping, okay, for a given metric that we use. In this case we are using self-distance, so another one, okay? Actually you can see on this small what does this means, okay? What does this mean when you do the projection, okay? So let me give you an example, which I think is better. Should I reduce it? No, it's fine. So here with this, so here in the mapping.head, we're just getting the head. So these are Panda structures, okay? So that we have a nice description. I mean, Tony already presented some Panda structures also for the protonation in the prepared protein. So basically, this is some nicely structured and with descriptions way of structuring the data, okay, array data. And here, when we do this self-distance, and normally we try to look at a given point in dimension, the first one that we look at, for example, the 0, it's basically we see the atom indexes that are related with it, and what does it mean? It's the distance between this C alpha of this residue, okay, which is residue name, residue ID, and this C alpha, so another C alpha of lysine 2, okay, and you see that it's a type distance, okay, and so on and so forth. So actually, there's a relationship between what we project and the actual molecule. So that sometimes when we go through the dimensional auto reduction and go through these projections, we can actually go back and try to see what it really means. What is distance that we're looking at? What does this projection really mean? Okay, and not being lost just in the models or just in the numbers. So this is a nice way of getting that information. So you can play around with the mapping, which is basically the Panda structure, okay, of the projection, and you can get, for example, what is the Christie 20 to 22. So just have. So this one is, for example, the 22 is the interaction between those atom indexes. It has the description, so it actually you can see various types, many types. So the difference here between iLock and block is because.
Well, here I don't have a range, so it's just a single one.
Oh, it's true, it's true. So yeah, this is the single one. Otherwise, the difference between iLock and block, well, it's a detail, so maybe I'm not going to do that. And here, for example, you can get just the description, for example, of the mapping, okay, specifically, instead of getting all the table, all the parts of it. So here it's another nice example of something that sometimes people do, which is dihedral angle. So here, by default, when you use the symmetric dihedral angles, it's going to do the 5 psi, okay? If you don't set it up to do something different. And here, sin cos equal false, you can see also the documentation. It just means that instead of outputting the sign of 5 psi, it puts it returns the angles from -80 to -180 to 180. Okay, so basically the same thing that we did for metric RMSD. So set up the projection and then do it on a molecule. Okay, project.mol, project mol. Okay, and then we can see again what we're seeing before. Okay, but not for dihedrals. Okay, so the first element, it's basically you have the indexes of the 4 atoms that are involved there, the description of which atoms there are, and the type of interaction. Here in this case is dihedral. This is really important then for the rest of the HTMD to guess. So from this type of data to guess other things in the Markov model and stuff like that, okay? Because, for example, to guess the sink or the source state in Markov models, but Stefan will talk about it later, okay? So this is the heading. You can see here that, for example, because of the caps, it just misses one of the atoms, okay? And the same in the tail of this. So this is it has so that you have a meaning of this. So it takes all the molecules. So basically, this means that this has 76 dihedral 5 sides, okay, on the molecule. So basically, probably is a 30-something residue protein, okay. So when you do this metric projection, metric dihedral, and then do the projection, you basically taking all the coordinates and just subtracting it to a very low dimensional space, which is just 5 sides. And this is normally very useful and normally something very widely seen, which is Ramakrishnan plots, where you just plot 5 psi, right? And you can actually do it from our data. So I think we are missing here something, no?
I'll just mention that the first and the last residue, they don't have, the first one doesn't have a fire, I think it doesn't have psi or...
So here we identified the diide.
No, this was before. This was before. It's in the project produces.
Okay. So basically, well, it's unfortunate, but you can see. So basically, it's with this piece of code. So basically, taking the information from the projections and turning it a bit, because it's just have to see that you want to ignore here, you want to ignore the time, so you have to do some flatten, and then there's something between doing the scatter between one every two. So if you go back here to the structure.
So in that array, essentially every second column is the pi angle, and every how do you say it? So 1, 3, 5.
The odd ones and even ones
exactly.
are each one phi and another psi. So taking the first and the last out, which is the first thing that we do, we drop the first and the last line, and then we just do every odd and every even one against the other, and we flatten so that we don't have time. And we plot it, and you can do a scatter plot from that, and actually you can already do something like which is resembles a Ramachandran plot. So with this, so we are using projections to get to lower dimensional spaces, and then working ahead with Markov models and stuff that we'll talk about. But you can still do the other stuff. And right now, in the near future, there will be a tutorial with this kind of things, because I think that people are still interested in looking into more of these things, even previous to doing Markov models. Maybe they want to see something that they're interested on to select things for doing, for example, adaptive or something like that. So I think that it's interesting, and well, it's just a continuous part of it. And Stefan will develop it further and considering more Markov models tomorrow. Okay, so I guess I'll pass to Jan. Oh no, so let's just slide. So you can also go to the documentation and see all metrics that we have available. Okay, so we talked about metric distance and self-distance, metric dihedral, metric RMSD, but we also have metric coordinates. Just returns the coordinates that you want, a selection of coordinates. Imagine that you just want C alphas. Okay, you can just return it. It's still a lower dimensional space than the entire system, so it's one of the simplest ones. And we have metric shell, which is the occupancy of an atom selection and another atom selection. Basically, it's some kind of RDFs, I guess. And then we also have metric secondary structure. We also have metric SAS, so we implemented it recently. And metric blend 2, it implements a bunch of metric that are also available in blend, right, Tony? Okay. All of them. Okay. Yeah. Accessible. Yeah. So yeah, basically that's it. The last slide. So Jenny, you can use it.
So I have a very 3 slides only, and then I'll pass it to Ma. It's actually the only place where you interact a little bit with the MD code in the entire HTMD. So it's 3 slides are enough, and all the rest is totally hidden to you. So you don't even know what sort of MD code you're running under. So
I forgot to do test after life and whatever. I don't know if you want full screen.
yeah. Okay, so very quickly, just starting ACEMD. So this is HTMD. So this is what we do when we pass from the build. So we saw before we build the system, and now what we do. We have a bunch of files there, and we don't really want unexperienced people to go through this file and choose which one is the correct one and so on. So we have decided to provide some best state-of-the-art protocols, which we think are reasonable, so to say, to equilibrate your system and start production run. And especially for the adaptive. So in the context of the adaptive, how do you do that? We saw actually there were lots of errors, even from experienced groups, in what are the Turing parameters, or what are these. So there are lots of parameters that you can set up in an MD engine, but there are actually a lot of sensible defaults which you really shouldn't even require to look at. And so that's more or less what we're doing here. So I just built quickly a system just to have something built. Again, trypsin, I remove benzamidine, I just prepare it, determine the segments, solvate and build. If you prefer Amber, you just comment the one before and you do the other one. And so these are the protocols, which are all available from HTMD.protocol. And we try to keep all version in case you like some specific version. But we add the new version every time. And so when we add a new version, we just change it version 2, version 3, version 4. So in equilibration, we are at version 2. And so you just have to import the protocol that you like. I think it's yes, to finish the other ones. And so equilibration has certain options.
As long as it's running, I don't think you can complete.
And first you can decide the runtime. You can decide the 4 nanoseconds in this case, the temperature. In this case, we don't use constant ratio, which is for membrane simulations. There is also a way to set up a flat bottom potential in the system. In this case, for instance, imagine you're simulating a GPCR and you want a ligand on the extracellular side. Because it's a periodic system, you don't really want the ligand to diffuse to the intracellular side through the periodic system. So an easy way to do that is to set up a flat bottom potential on top, so that particular box, so that the ligand doesn't move out of this box. So, for instance, you could set up a box which just stop the ligand from going. So in a flat bottom potential, it's usually flat, and then there's some harmonic potential, so a spring. And in this case, so what are the things that you set here? So you set a reference, an origin, for instance, because the GPCR might move by diffusion during the simulation. So you say my system, my box is centered in this atom, and then you set which selection, the flat bottom selection, you're applying the flat bottom potential, in this case, the ligand atom. And then you say how big this is, so it's minus 25 to 25, it's minus 25 to 25, and from 43 to 45 Armstrong. So practically, we are in this way constraining the ligand between 43 and 44 43 and 45 Armstrong in a very tiny slab on top of the GPCR, which is useful for equilibration. You just want the ligand to stay up there while you equilibrate it. You don't want it to go anywhere. The 25 to 25 is enough to just keep it on top of the GPCR. You might want that or not. You might just say the entire box. And then this is the flat bottom constant. So when the thing becomes parabolic, how much do you want? And that's about all you need. There are other parameters that you can change. So for instance, if you want some constraint on some parts, you can constrain. In this case, the default is to constrain the carbon alpha with 1, and all the other non-antigen atoms with 0.1 kilocalmole. Again, we apply a constraint on every atom, so that an harmonic potential on every atom on the initial coordinate, and we decided that it makes sense to apply a stronger constraint on the carbon alpha and a lighter constraint on the other non-hydrogen atoms. We will leave totally free the hydrogen. And there are some other settings, like the number of initial MBT steps and so on and so forth. And so when you do, so we set this up, and then you say, okay, I build my stuff in this directory, build charm, and I want you to generate an equilibration directory. So in HTMD, there is this concept to be general and not be code dependent. We have this concept of simulation directory. So I so I run a directory practically. And I assume that inside the directory there are all the files that are required to run the simulation. So I don't have to be ACEMD dependent or Bromax dependent or whatever. This is what makes the type code general. So you can run this, and this will create this equilibration. Remember, in the charm build, in the build charm, there were all these files, like 15, 20 files, and it wasn't obvious which one to pick. But if you do everything inside HTMD, then you'll have just an input, parameters, structure.pdb, structure.psf, and some run.sh, which is what you should run. And the default run.sh runs ACEMD, but it would be easy to do for other codes. There are some implementation that have been done by some imperial guy for PMEMD. And there's, I think, we're also looking at Gromax now with some other guy. The only thing that, especially for PMND, we cannot test it, so there will be some sort of contributed file so that you can use, but we're not sure if they do the right thing or not. So we're happy if you use it, and then it will be there. So in this case, there is the input file, and that's the directory I want to run. And because I'm on a GPU machine, I can simply do that. So let's go back. So let's be
put another 0 there.
That's fine. No? Let's do that.
Depends on the size of the system.
Let's recognize femtoseconds here or in nanoseconds?
You should recognize femtoseconds as well.
You could do the steps.
Okay, I do a very wrong, maybe it's equilibration, just 1,000 femtoseconds. This will just rewrite the equilibrium file, update the input file for ACEMD, which I'm not even going to show you how it's done. And then I run it. There is this concept of queues, and which Stefan will talk about. Practically now I'm running on this workstation. Stream is running, and it's asynchronous running if you want, but we put a wait so that it's waiting for it to finish so that I can start to do the other stuff later. And you can run on Amazon if you have AceCloud, so if you have ACEMD platform. You can run on your queuing system. We support Slurm, LSF, PBS already. And so there might be some minor adaptation that you need to do for your system, but this should work. And it's actually been used already, like we use Slurm in the lab and some other use of it. And this should stop now. And,
good timing.
So now the simulation are finished. This is finished since I can move on. Really should have been a long simulation, but then I have the production run. The production run at the moment is a bit unclean. We're doing some ACEMD specific configuration. But I mean, it's okay, so it's very small. So again, here we say we have a runtime of 10 nanoseconds, units of 10, temperature 300, pin coordinate to extend the system. So we say we want to take as input, the input coordinate, the output, which was in the equilibration directory. And we want to take the box size, again, from the output of the equilibration directory. And all the rest remain the same, so the parameter and so on and so forth. And again, you can decide the flat bottom also is available here. Maybe here you can use a larger flat bottom that's very big that enters into the membrane. So the ligand is free to move everywhere in the extracellular side, even hit the membrane. And that's it. So this will now generate the production directory, and then you can use that as generator for your adaptive. So all what these things is doing is hiding a lot of complexity, especially in the equilibration. Because in the equilibration we do a first step of minimization, then we do we reduce the constraints slowly, At some points we cut the constraint totally, we start the NPT, we equilibrate that. So all these steps they use some defaults, like which you can change, use an equilibration protocol, but they're usually fine, even for membrane protein. And so they practically hide from you all the complexity of the input file, especially in ACEMD. For doing the flat potential, we use some TCO to keep to implement the flat potential and flat bottom potential, and you don't have to look at it. It's similar to what you have with charm build and number build. All the files are there. You can check it, modify it, and do whatever you want. But actually, we can run the entire workshop without having even to show the ACEMD manual, or any manual for what it matters of any ND code. You just run like this. And that's it today. 2 minutes. Yeah, so
I don't know if you want to also, I remember this thing is also, if you don't like the protocols are standardized, but if you have your own protocols, the advantage of HTMD is that you can also solve around your own protocols and build your own based on that. And I think that's flexibility also is good. If you want to have your particular protocol or something like that, it's also possible.
Yeah, you can do that. Of course, you can do that. Yeah. At the moment, there are only these simple protocols. There could be more complicated one. I thought there would be a lot of protocols actually at the beginning, but we just use these two all the time because we didn't need to really do one protocol for membrane protein, one protocol for so with this one it works fine, or on anything.
How do you get around the pressure trying to double island? I mean, I remember looking for max and you know, you have this semi-acid.
Yeah, that's fine now with the normal aerostat. There's no problem.
Really?
Yeah, you just run it and
same aerostat for the local system and for membrane.
Yeah. No, there's no different. There's no need to do the social extension thing anymore. The force fields are okay now.
The only difference is the constant ratio.
Yeah, you just add that constant ratio thing. Yeah. So when you're in the equilibration, there is this constant ratio, which means that you don't want the 3-dimension when you apply the pyrostat to change independently, because you want to keep you want the x and y to be maintained in scale. So if one grows, the other one grows proportionally, and that's the only really change between the membrane. And
so you have to explain the first comment, so what the popular one.
No, that's what I'm saying. It works, but the only thing I do is an option. Yeah, you have to change that option. We put there in comment for membrane, use that, because it's practically the only thing. And then you need to run a bit longer, maybe than 2, 4, 5 nanoseconds. Maybe you want to run 20, 50 nanoseconds, 100 nanoseconds for membrane protein. And